Welcome to Data 102. My name is Ramesh Sridharan, and I'll be one of the instructors for this class. We're really excited to have you here with us this semester. Data 102 is meant to be a capstone class on your undergrad data science experience. So in this class, we're going to cover a lot of big ideas in data science that really build on the fundamentals that you've learned in Data 8, Data 100, and other data science classes. So we're going to center this course around two big ideas. The first is, how do we make decisions when we have uncertainty? That is, how do we use data science to help us make good decisions when we're uncertain about the state of the world? And what consequences do those decisions have? How do we understand and work through the consequences? How do we make sure that those decisions are shareable and understandable by other people, and so on? The second big idea that we're going to look at in this class is, how do we build models that work in the real world? So what are the assumptions underlying models that we use? And what happens when those assumptions break down? So how robust are our models? So these questions aren't new to you. You've been thinking about them since you took Data 8, since you took Data 100 in your statistics, computer science, broader discipline classes. And you've probably been thinking about these ideas even before you came to Berkeley. But what we're going to do in this class is we're going to cover some advanced topics in data science that really get at the heart of these two questions. And so a lot of the topics that we cover in this class are not typically covered in an undergrad class. A lot of this is usually covered at the graduate level, usually has pretty extensive math prerequisites. But what we think that these ideas are really important, and they're really important for you to know if you go out into the world and practice data science, whether that's in industry, academia, policy, no matter what you do, these are really important ideas to understand in data science. So what are we going to cover that helps us answer these questions? Well, some of the topics, I know there's a long list here, I'll kind of walk through. So first is frequentist versus Bayesian modeling, right? You've kind of learned about this distinction a little before, but we're going to learn what kind of assumptions each philosophy takes to modeling, and then what kind of inference algorithms that leads to. So how does, what kind of theory of decision does it lead to when we use a frequentist model versus when we use a Bayesian one? We'll learn a lot more about causality. So by now, of course, you've heard, oh, correlation is not causation, but, or correlation does not necessarily imply causation, but we'll learn a lot more about how we can decide whether one thing actually causes another. And we'll look at what assumptions we have to make in order for us to make that decision. We'll talk a lot about regression, confidence intervals, bootstrap. These are ideas you've seen before. We're going to go a little deeper into them in the context of this kind of like decision-making and understanding modeling assumptions point of view. We're also going to look at what happens when you need to make repeated decisions. A lot of machine learning gets framed as, oh, like you get a data set, you train a model, and then, like as new data comes in, you just keep on making predictions and the model stays the same. But in the real world, as you get more data, you learn more about the world, and maybe you should be changing your model, right? Maybe the world is changing, maybe you just learn more. Either way, we want some way to incorporate feedback into our models. And so we're going to look at a couple of different approaches that help us understand what happens when we need to make the same decision over and over and over, or similar decisions, and we get feedback on how well we're doing each time. So we'll talk about bandits, we'll talk about reinforcement learning in that general area. We'll also talk about robustness and generalization. So when we build a model, or when we formulate some way we think the world works, we want to know, how robust is that model to violations of the assumption, right? Like if I say, well, I think that there's a linear relationship between these two variables, and it turns out, well, it's not actually linear, it's like kind of linear in one area. Well, what happens? We'll dive a little deeper into interrogating those assumptions, looking at how robust our models are. If we think that the variance is uniform across our X variable in a regression, which is kind of a standard assumption for linear regression, what happens if that gets violated? So we'll dive a little deeper into those kinds of questions. And then last but not least, we'll talk a lot about topics that are really important for taking these decisions that we make in data science, and we'll kind of step back from the kind of like mathematical understanding of these topics and into, well, what happens when we want to take these decisions into the real world, right? If your model makes a bunch of predictions and you want to use that to make a decision, well, that decision is going to affect people at the end of the day, right? At the end of the day, pretty much every decision that every prediction that every model makes, and every decision that somebody makes with that prediction affects real people in the real world. And so if you want to take your model and convince people that they should trust its predictions, a lot of times people will ask for interpretability. They'll want to know, why did that model make that decision? Like, why exactly did you come out with this? And so we'll talk a lot about ways that we can interrogate and understand the predictions that our models are making and help us make better decisions from those models. We'll also talk about privacy. We'll talk about some formulations that help us understand, well, how do we have like a computational framework that lets us think about privacy in data and in decision-making. So that's all for the overview of this course. In the next video, we'll talk more about some details of the history of data science.
So let me talk a little bit about a perspective on data science. This is my own. I've been working in this field, roughly speaking, for most of my career, which is now like 30 years. So I have some perspective I want to offer to you. Your first reading assignment is going to be an article I wrote that I put up on Medium about 2 years ago now. It's called Artificial Intelligence, the Revolution Hasn't Happened Yet. I wrote it for kind of a bigger public, but, you know, kind of trying to be a bit of a help people, say in public policy or in information technology or whatever, think about the implications of what we're doing and what we're working on. And I really want to encourage you to read not only that, but there's also some commentary by a number of well-known and very thoughtful people. All right, so first of all, I think data science is the most exciting thing I've seen in academia for a long, long time. Sort of everyone on campus feels they belong to it in some way. Most people feel like they're trying to use data to explore some phenomena, and they have a perspective on that, and it really is a big umbrella. More so than the more technical fields that have kind of had similar material in the past, like machine learning or even AI. It includes people like in physics who have lots of data, or people in sociology who are interested in using data to understand human behavior, people in neuroscience, linguistics, and so on and so forth. I see it as having arisen both in science and technology. So science, maybe 20 years ago, there was like the Genome Project, there was astronomy generating lots of data, and there was what is sometimes called the fourth paradigm of using a lot of data to do science, not just kind of working out a mathematical formula and testing that one formula in a hypothesis test, but really using a lot of data to try to perceive new phenomena, discover new phenomena that's maybe highly contextual. So that was in science, but really around the same time, now we're talking about the 80s or 90s, new technology and new business models arose. Amazon is probably the best example of this, where they were trying to do things like model supply chains to make sure that products, billion product could be served up to hundreds of millions of people. And so you had to take in a vast amount of data and model that data to be able to make those kind of predictions and to actually build the logistics chains. And then to give people the things they want, do things like recommendation systems. That arose in that era. And then, Google and Facebook and all had an IT model that involved lots of data, analyzing what's on the web and how people connect and so on and so forth. So in that era, technology started advertising for data scientists. I think the term really started to get to be used more in technology than in academia. They were advertising for jobs for people who could both program and do statistics. And obviously somehow problem solve, not just come in and run some formula. And so I think that's really been striking. Lots and lots of people have gotten hired as data scientists, and some of the more interesting jobs have been in data science to this day. And that's going to continue for a long, long time to come. All right, so that's one set of comments. Another one is that if you look back in history and ask, when has there been a similar era, a similar kind of phenomena that's kind of a large scale, that involves lots of people, lots of new jobs, a different kind of technology and so on. And I think a good example are when other, fields arose that are now called engineering fields. And my favorite example is chemical engineering. So my father was actually a chemical engineer, and I know that in the 40s and 50s, that was the exciting thing to be. There wasn't computer science yet, and so on, but it was exciting. It was like the people were going to build factories that were going to create products that could, like chlorine in swimming pools to make sure that, people didn't die of bacterial infections anymore in swimming pools, or make plastics so that we could build all kinds of new products, and so on and so forth. So there's been good and bad in chemical engineering, but, a lot of good. A lot of our world would not be the same without the kind of products that those people made available. And before chemical engineering, there was chemistry, the ability to understand what happens when you pour one test tube into another. There was quantum physics, there was fluid flow. So there's kind of an understanding of the stuff of nature. But the idea that you could take all that and build it into a factory, at scale, you could do the thermodynamics that you needed, the temperatures, the pressures, the volumes, and the flows, and it would actually not explode, and it would create real product economically viably. That's non-trivial. And so people in the 30s and 40s tried to do this, and a lot of factories didn't work. They either just didn't start, they didn't make any product, or they've exploded, and a lot of people died in accidents around factories. And so a field emerged called now chemical engineering, whose job it was to give specifications of how you would build such factories, how it would work, how it would be safe, and then ideally how it would not create new problems like pollution. But there was problems, right? New problems emerged. And I think electrical engineering, civil engineering, I know less about the history, but I think they're similar. Electrical engineering already in 1880 or whatever. There's Maxwell's equation, so sort of everything is understood about electromagnetism, electrons that in science that you need. But to build the field where you could power a city, or you could bring things into your home, or you could have circuits and all that you needed a whole new field, and that field emerged slowly as people started to build things. And again, there were dangers and failures along the way. Houses burned down and so on. But eventually a field emerged called electrical engineering. All right. Civil engineering, same thing, buildings and bridges and so on. So now we kind of look at this in our era and say, well, that's great. That's engineering. It's kind of now very systematized and maybe not as exciting anymore. And it's not science, right? It's different. It's engineering. And the word science has become more prized than engineering. So if you say social science, that's clearly a good thing, right? To study the science of social interactions. Social engineering sounds terrible. Genome science sounds good. Genome engineering, not so clear. Mathematical science is a thing. Mathematical engineering, that doesn't sound like anything. So I'm making somewhat of a provocative point here, but I think of what we're doing, even though we're calling it data science, and one part of it does help science, and somehow it's supposed to be mathematical, it's not all that different from the mathematics of electrical engineering or chemical engineering, and it aims to build real-world systems that somehow make human life better. So if you think about a system that's doing the response to the COVID epidemic right now, that is a big worldwide planetary system that brings in data, helps make experiments happen, helps make decisions, helps individual doctors, helps people know what to do. It's all ad hoc right now. It's not been designed, but it's kind of up and running at some level. Systems that do commerce, Alibaba, Amazon, and so on, are data-oriented systems. They're like factories that use human data to do things, and so on and so forth. Transportation, finance, and so on. So our world is kind of now more and more full of these kind of systems, but they've been all built in very ad hoc ways, and they've created lots of problems. There's not really maybe explosions, but the Facebook problems, those are real problems. And good engineering-oriented people shouldn't have created those problems. They should have been aware of that, and should have brought that into their thinking as they were building these kind of systems. So I want you to be, at least, if not embrace the term engineering, be aware that maybe it's not a bad word to describe part of what we're doing, because engineering is kind of systems that work in the real world and deliver value to humans. But we're pretty far away from that, I think, arguably. We're really at kind of the stage of the chemistry and not the chemical engineering. All right, so just a little bit more background on this. The other terms that you'll hear bandied about are like machine learning, artificial intelligence. Machine learning really was a term that arose in the 1980s. That got at least more popular then. It's kind of a computer science term about, instead of having to program computers, can we just have them learn from experience? But the ideas that were actually developed are kind of mostly statistics ideas, decision trees and classifiers and so on and so forth. So how is it different? And there's been a lot of argument about that. For me, it's helpful to think about it as kind of an engineering side of statistics. You're trying to build real systems in the real world. That's what machine learning people like to try to think of themselves as doing. So it's not a new field entirely, but it's kind of like chemical engineering is to chemistry. And I already alluded to this, but let me just say a little bit more about the history. If you think about the 1990s, there was companies like Amazon that were doing fraud detection for, like millions and millions of transactions, or really billions. And they're using data analysis and really what we now call data science to do that, and modeling supply chains and so on and so forth. Then maybe 10 years later, they start to notice that a lot of the data is about human beings, like they're doing recommendation systems. What do humans like? How can we help them find things they like? And now maybe 10 years after that, there's kind of a lot of focus on pattern recognition. You're using these systems that were already built for other purposes, and now you're kind of retooling them to take in data like speech or vision and have humans label this data, or translation from one language to another, and then have the computer learn to mimic the human. And this here is now often being called AI because it's mimicking humans and it seems human-like to some level, but really, if you know what's under the hood, it's not very human-like, and it's pretty limited mimicking of humans. But it definitely is a very powerful form of pattern recognition. Now, I personally view what's emerging is more than just pattern recognition. It has to do with decision-making of lots of decisions by lots of agents, humans and computers all connected, planetary scale, not just a single computer that's smart and solves the Turing test, but rather kind of a network that's global that does things like helps with medical problems or whatever. So market ideas start to come to play, where people interact in certain ways, and everybody can't have just exactly what they want. They have to have trade-offs. Trades need to happen, and so on and so forth. And if you're interested in kind of the research side of this field, to me, this is where many, or if not most, of the problems reside. It's in this kind of networking of learning systems area. AI is another buzzword. I just want to mention it briefly. It's been the more classical term for kind of machine learning is viewed as part of AI. I personally don't view it that way, but just if you will look at this article that's referenced at the bottom there, you'll sort of see my own perspectives. And I, noted that AI was classically in the 1950s this human imitating aspiration. John McCarthy associated with this idea that we'll have a computer imitate a human. Another perspective that arose sort of more in the 60s and 70s, Doug Engelbart, was that computers are there to help augment human intelligence. And so a search engine arguably does that. It helps us be smarter. And now what I think is kind of emerging is a little bit more of this networking infrastructure around us, which is intelligent. So it's not just about a single computer being super smart. It's about a whole infrastructure where the infrastructure is getting smarter. Okay, and just to say a little bit more about this pattern recognition, third generation of machine learning has focused on pattern recognition. So if you take the class 189, that's kind of the focus of that class. You'll learn about classification regression, neural nets, and so on and so forth. It's become a commodity. There's software you can download to do it. And you could and should learn about that kind of software, and you should learn how to do neural nets and pattern recognition. Take 189, learn it on your own. It's not that hard nowadays, lots of tutorials. But the current class is aimed at complementing that perspective. It's aimed at adding the notion that to pattern recognition, you also need to think about the decisions that are being made based on the pattern recognition. That it's not just enough to recognize patterns, you have to think about what are the consequences of my recognition of patterns. All right, so classically, this is done by thresholding an output of a pattern recognition system, like a neural net. So let's think a little bit about that in a real world domain. So let's suppose that we're going to give lots of medical examples, by the way, this semester, partly because of the COVID epidemic. In the past, I would say, this idea would be appropriate if an epidemic were ever to come, and now an epidemic has come. And so we're going to use examples like this. But let's sort of gear up a little bit by just thinking not about an epidemic, but just by a regular good old-fashioned checkup in a doctor's office. Within 5 years, you'll go into a doctor's office, and they will probably measure 50,000 variables about your body, maybe including your genome. And that vector, 50,000 dimensional vector, may go into a really big learning system like a neural network. and it will have been trained on lots and lots of data, maybe all the world's medical data. And so in some sense, you might argue that it's supposed to replace a doctor. I hope that you will agree that's far-fetched. That's not going to happen. And all right, but think about the usage of such a system. Suppose you go in and you put in all the data about yourself, and one of the outputs is a prediction about whether you're going to have kidney failure or not. Okay, there's many outputs. Some of them are about the heart, the liver, or whatever. And suppose that number comes out to be 0.701 for you. And based on the classical data, the threshold of 0.7 is what's used to kind of threshold people who have kidney failure versus those who don't. And so now the doctor looks at you and you look at the doctor and you say, whoa, am I about ready to have kidney failure? What should I do? That's not a decision. That's not the decision you should have an operation or the decision you should even take medication. It's the beginning of a dialogue with the doctor. You're going to ask things like to the doctor, what are the error bars on that 0.701? And I hope that data scientists like you folks are aware that error bar is a complicated idea. It's not just a confidence interval. It's about all the uncertainty that arose when you gave me that number. Like, what data set was used? Is it an old data set? Is it a recent data set? Is it a data set about people like me? Or is it about a different kind of person who's not really so relevant to me? Where did that data come from? What's its provenance? What kind of measuring device was clicked on? So on and so forth. The answers to those questions are critical because they will change the confidence you have about that 0.7. There may even be bias in that 0.7. It really was a 0.5, but there was a bias. These are all the kind of issues that you would start to get at in a dialogue with your doctor once you've been scared that you might have kidney disease. You're also going to ask like kind of so-called counterfactual questions about, hey, are you really aware of certain things about my family? In fact, I wasn't even aware of that thing until I remembered it in this moment that, I had an aunt who had kidney disease or something else. Or what if I were to exercise more? What if, can we get a second treat option? Those are questions that aren't answered just by the data alone. They're answered by thinking about other data you could have gathered or other data you might go gather and then put it together and so on. So that's what a real decision-making system starts to be. It's a real dialogue. And so we're going to teach you some things this semester that have to do with that dialogue and about how do you ask these kind of questions, what are the kind of algorithmic ideas, and how do you bring other kinds of context to bear when you think about decisions. Okay? Now, decisions are rarely just one decision at a time, and they're almost always in some context. So I've already elaborated a fair amount on the context of a one decision in a doctor's office, all the things around it about diet and history of the data and so on. All right, but when you start thinking about all kinds of real world decisions, about, what kind of, factory do you build? What kind of, job benefits do you give to people? How do you do certain kinds of health plans or treatments or whatever? All these things that start to make life and death differences to people. You ought to start to ask all these questions, and you realize that it's not just one decision. It's often many decisions. Like today, I made many decisions that were kind of consequential, not just one. And those were related decisions. And I want to think about them as kind of related and make sure that the overall set of them were pretty good, not just that each individual one had a low error or something. And moreover, that network is not just my own decisions. I had my family make some related decisions too. And there are other people related to me. We all live in a big network where we're all making decisions, and we're really sensitive to and influenced by the decision-making of other people. What resources might they use? How does that affect our usage, and so on? And so now we're starting to talk about things like scarcity and competition. And this doesn't necessarily mean that we're like in a dog-eat-dog world. It just means that, for example, if I want to get to the airport quickly, I got to go down a certain street. And if you have too many people going down that street, then we're going to have congestion, and none of us will get there quickly. That's not too good. So this starts to get into the field of economics. Economics study, it is the field that studies scarcity and competition in the context of making decisions. And so if we're going to be good data scientists, we can't just talk about the data and how we format it and how we put a line through the data and even the error bars. We've got to start talking about, well, what are the consequences of this? What decisions are you going to make with this system you're building? And how's that going to interact with other decisions in the real world where there's often notions of scarcity? All right. Moreover, decisions often have an effect on your future. Like, what future data should I gather? Should I go to do I want to go to a different kind of job? How should I get the data that tells me what job is best for me? How do I think about all those things? And our systems, if they don't do these kind of things, are going to be really poor. We're not going to trust them. They're not going to really be very helpful to us. And then finally, there are obviously decisions when there are consequences for others and a need for an ethical perspective. It's not just about scarcity and competition that, you know, we want to give everybody the best, you know, according to their own value or utility. There's also laws. You can't do certain kind of things. It's wrong. We all agree. It should never happen. And so whatever systems we build should respect those laws and understand them, and we should be able to evaluate whether they're going to respect those laws. Okay, even broadly, more broadly speaking, I want to just have a quote here from someone named Ursula Franklin. She is a really kind of an amazing person, a real thought leader, worked in, I think, originally metallurgy, but then became a social scientist. And here's an example of the kind of thing that Ursula Franklin said about technologies are developed within a particular social, economic, and political context. They arise out of a social structure that are grafted onto it. They may reinforce it or destroy it, often in ways that are neither foreseen nor foreseeable. So this is even broader than what I'm talking about, but certainly in the same spirit, that there is a context, and it may be very hard to understand the consequences of your system in that context, but you better think about it. And similarly, here's a second quote: context is not a passive medium, but a dynamic counterpart. The response of people, individually, collectively, and the response of nature are often underrated in the formulation of plans and predictions. Okay, so this is very much in the spirit of the kind of things we want to do in this course. Now, a social scientist might be more interested in kind of the science here of understanding these phenomena and documenting them. And we are a little bit more mathematical and engineering, or we want to kind of build systems that help with these things, that help to solve problems, but we have to be aware of the consequences of the things we do. I want to just highlight this game theory issue here. We're going to be talking a bit about economics and game theory around the middle of the semester. And I just want to show you kind of a particular cute little example. So economics and game theory has often to do with, well, if I make a decision of some kind, maybe I want to incentivize some nice behavior on somebody, you know, like my children's part or somebody else's part. But they're going to look at what I did, and they will have their own reaction. And I should be able to, I need to anticipate that often, because things may not go exactly the way I planned, and I better have that in my thinking. I better at least go 2 or 3 steps down the tree of decisions and consequences. And so here's an example of King William III back in 1696. He wanted to tax people in England, and it's kind of hard to figure out how to tax people so they don't hide their wealth in various ways. And so he said, well, here's a good way that everybody has a house, or at least many people have a house. And so I'm going to tax the windows in people's houses, the number of windows. So it sounds like a plausible way to do it. You know, if you're more wealthy, somehow you're going to have a bigger house, it'll have more windows, and you can't not have windows, right? But I think you may know what happened. As the idea spread around, I think this picture is, well, it's probably in the South, like in Italy, where people really love to adapt. But here's a house that, you know, they boarded up their windows, and you'll see a lot of these in Europe. And what happened is that people boarded these up because they had to pay less tax. And so that wasn't a desirable outcome. But this kind of thing that happens all the time. I'm going to give another example that I forgot to prepare a slide for, but this is actually Edinburgh. I forgot to prepare a slide for, but I wanted to mention it. So one of the markets that was sort of created by information technology in the last 10 years, that's not a very good market, but it's at least a glimmerings of one, is Uber. So Uber, you know, it is a connection between producers and consumers. The producers are the people who have a car, and the consumers are people who want to ride. And the Uber platforms connects you. Now, if it was really a good market, there would really be kind of an auction mechanism, and there would be back and forth on both sides and all that. So it doesn't do that. But it tries to kind of incentivize, you know, it has a pricing system and tries to use that in a smart way. Well, there was an example where I think it was at Los Angeles International Airport, where the Uber drivers would all get together, and there would be a text which would appear on some website, maybe Facebook, maybe Piazza, I don't know, where all of a sudden all the Uber drivers would shut off their phone. All right. And now the pricing mechanism would kick in. It would see there's no supply of Uber drivers at the LA airport. And so the price would be raised very much higher to try to incentivize drivers to go to the LA airport. The price goes up a whole lot. And, you know, people start punching the button because they need a ride, and they're willing to pay this higher price. And then suddenly the Uber drivers all turn back their cell phone on, and they get those high prices. So that's, a collusion example. And it's exactly the kind of thing that happens if you build a decision-making system where you didn't think, too far ahead about the kind of consequences of the decision-making system. Here's kind of a law. This is an economics kind of story, which is that entity observed regularity will collapse once pressure is placed on it for control purposes. I mean, if you see something out there in the real world and you say, well, this is what I want to incentivize people to do, I'm going to, try to get you to optimize this quantity, people will find ways around that. And so here's a little example. This is from Moritz Hart last semester. This is his slide, where here's a particular study that people did. They're trying to predict credit repayment. So they're going to, decide whether you're credit worthy or not. And they're looking at your mobile phone usage. So they're doing a machine learning problem here. They're gathering, or data science, they're gathering features like number of outgoing calls you made, how often do you respond to texts, your average airtime balance, the entropy of your GPS coordinates. In other words, how much do you move around? That's a particularly interesting one, right? And so then they built a predictor based on that, and they argued they could predict your credit repayment. But now, as soon as you make people aware that this is happening, or they figure out that it's happening, ideally you should make people aware that things should be transparent, right? But as soon as you do that, you can ask, what do people really do? And here's another example where this entropy idea is even brought in the picture more clearly. Here's an offer that if you download the Oscar app, someone had built an app, to your phone, and you sync Apple Health or Google Fit to track your steps, you're going to earn rewards, okay, when you meet your step goals. So this is some, IT system that's trying to get people to sign up for something, and they're going to give them $1 a day. All right. So people, how did they behave? Well, there's two ways of going back. Some people put on the device on their and started going out and meeting their health goals, and they made some money, and they were really super happy. Other people found a way to build a little device that would move their cell phone around, all day long, and reap the rewards without them having to do anything. So, great examples of that.